In this video, we apply the small signal analysis we have learned in the previous videos to the common emitter configuration. We use the hybrid pi model for small signal, and we see the voltage and current gain, the output and the input impedances. We see also how to choose the value of the bypass capacitor. We saw in previous videos the biasing of the circuit and the pi model of BJT, calculating R pi and GM, which are functions of the bias collector current and the bias base current. We remember that we can use the pi model under the small signal hypothesis, so only if the input signal is much less than the thermal voltage and the input signal is at low frequency, where the beta is constant. Now we want to calculate the gain, the input and the output impedances. We remember also an important result we found in the bias in this circuit, and that is putting the resistor Re in emitter to make the collector current independent on the beta, and for this reason we properly chose the resistors in order to make through this relation. So now we add to our pi model the other circuit elements. First, we remember the C1 and C2 are coupling capacitors with the purpose of decoupling DC signal from AC signal, and so we have to size them properly in order to make them a short circuit at our work frequency. So in the AC analysis we set them a short circuit. Now we remember that for the superposition method we can do the AC analysis setting all the DC voltage sources to 0. So this is now the AC circuit, in which we see that between the emitter and ground there is Re, and we see that R1 and R2 are in parallel and they are both between the base and the ground. We see also that Rc is between the collector and the ground. Now we can calculate the voltage gain. We can write that V out is I out times Rc, which is minus Gm V pi times Rc. We can write that IE is the sum of IB and IC, getting this equation because IB is V pi divided R pi and IC is Gm times V pi. We can write the equation in this way, remembering that R pi is beta divided Gm, and because 1 divided by beta is much less than 1, the equation becomes this. In other words, we say that IE is equal to IC because IB is much less than IC. Now we should relate V pi to V in, writing the Kirchhoff voltage law to this circuit. So we can write that V in is the sum of V pi and VE, so IE times RE, which becomes this, remembering IE is equal to IC, so GM times V pi. Now we have V pi as function of V in, so remembering that V out is minus GM RC times V pi, we have that V out is this, and the voltage gain, V out divided by V in, is this one. If GMRE is much more than 1, the voltage gain is equal to minus RC divided by RE. This voltage gain is stable but usually is not high because for biasing issues it's difficult to set RC much bigger than RE, I mean hundreds times bigger. In order to improve the voltage gain, we use a bypass capacitor. In this way, we don't affect the biasing point in which we need emitter resistor, because the capacitor in DC is like an open circuit, but in AC, if it is set properly, it behaves like a short circuit. So remembering the impedance of the capacitor is this, I want it much less than Re. If, for example, Re is 1.5 kilo ohms and the working frequency is 1 kilohertz, I want Xc at least 20 times less than Re. So the capacitor value has to be more than 2.1 microfarad. In this way, we can easily bypass the emitter resistor, leaving it only for biasing purpose. The circuit in AC is like this one. The related pi model is this one, where we add in input the parallel of R1 and R2 and in output RC. The voltage gain in this model is easy to calculate because V out is minus Gm times V pi times Rc, but V pi is equal to V in, so the voltage gain is minus Gm times Rc, which is higher than the previous configuration without the bypass capacitor. For calculating the current gain of this configuration, we use this pi model in which IC is beta times IB, so I out is minus beta times IB. I in is IB plus IE, the current flowing into R1, R2, which is equal to the voltage drop V pi, or IB times R pi, divided by R1 parallel R2, which we can write in this way. Now we can have the current gain, which is I out divided by I in, so it is this. If the parallel between R1 and R2 is much more than R pi, the current gain is more or less equal to the beta. So we have an high current gain taking into account the bypass capacitor. Now we see the input impedance of this model. First we calculate the impedance looking into the base and we call it ZB. ZB is equal to VB divided by IB, and remembering the Kirchhoff voltage law in the base emitter circuit, we can write this, which becomes this one, remembering that V pi divided by IB is R pi. So this impedance ZB is in parallel with R1 and R2, so the total input impedance is this. If we take into account the bypass capacitor, RE is short-circuited, so the input impedance becomes this one. The output impedance is the impedance looking into the output when all the independent sources of voltage and currents are zero. So Vin is zero, and if Vin is zero, V pi also is zero, because Vin is V pi plus Gm V pi times Re. So if Vin is zero, V pi also is zero. And if V pi is zero, Ic is zero, being Ic equal to Gm times V pi. In this circuit, the output impedance V out divided by I out is equal to RC. Remembering all our results, we can see that this configuration has a medium voltage gain and an high current gain, so an high power gain, which is the product of the current and voltage gains. It has a medium input impedance and an high output impedance. This configuration is usually used for amplification at low frequency. Please leave me a comment, let me know if you liked this video. Make sure you put a thumb up, click the notification bell and subscribe to my channel.